The increasing demand for lighter, stronger, and more fuel-efficient aircraft highlighted the limitations of conventional metallic structures such as aluminum alloys. Although metals offer good strength and manufacturability, they are prone to fatigue, corrosion, and higher structural weight. Composite materials were introduced in aircraft structures to overcome these limitations by providing superior strength-to-weight ratios, improved fatigue resistance, and enhanced corrosion resistance, thereby improving overall aircraft performance and efficiency. Composite materials are engineered materials formed by combining two or more distinct constituents to achieve properties that cannot be obtained from the individual components alone. In aircraft composites, these constituents typically consist of high-strength fibers that carry the primary load and a surrounding matrix that binds the fibers together, which transfers loads between fibers and matrix and protects them from environmental damage. The resulting material exhibits tailored mechanical properties suited for specific structural applications. The most commonly used composite materials in aircraft structures include carbon fiber reinforced polymers, CFRP, glass fiber reinforced polymers, GFRP, and aramid fiber reinforced polymers, AFRP. Carbon fiber composites are widely used in primary structures due to their high stiffness and strength. Glass fiber composites are used in secondary structures for their impact resistance and lower cost, and aramid fiber composites are preferred in applications requiring high toughness and damage resistance. Composite aircraft structures are generally anisotropic, meaning their mechanical properties vary with direction. This characteristic allows engineers to tailor strength and stiffness by orienting fibers along specific load paths. Composite components are often manufactured as laminated structures consisting of multiple plies stacked at different orientations, enabling efficient load distribution and improved structural performance compared to isotropic metallic materials. Composite structures offer several advantages, including significant weight reduction, high strength to weight and stiffness to weight ratios, excellent fatigue resistance, and immunity to corrosion. Additionally, composites enable the integration of complex shapes and reduce the number of mechanical fasteners, leading to smoother aerodynamic surfaces and reduced maintenance requirements. These benefits contribute to improved fuel efficiency, increased payload capacity, and longer service life of aircraft. Despite their advantages, composite materials present certain challenges in aircraft applications. They are generally more expensive than metallic materials and require specialized manufacturing processes and quality control. Composite structures are sensitive to impact damage, which may not be easily visible on the surface, necessitating advanced inspection techniques. Furthermore, their anisotropic behavior and complex failure mechanisms require sophisticated analysis and design methods. Composite materials are extensively used in modern aircraft for both primary and secondary structures. Typical applications include wings, fuselage sections, control surfaces, tail structures, fairings, and interior components. The increasing use of composites in aircraft design reflects their ability to meet stringent structural, performance, and environmental requirements in modern aviation. The Boeing 787 Dreamliner represents a major milestone in aircraft structural design by becoming the first large commercial aircraft to use composite materials as the primary structural material. Introduced in the late 2000s, the Boeing 787 demonstrated that advanced composites could significantly reduce weight, improve fatigue and corrosion resistance, and enhance overall aircraft performance. As fuel costs increased and environmental regulations became stricter, aircraft manufacturers sought materials with higher strength-to-weight ratios than aluminum alloys. Traditional metal structures were limited by fatigue cracking, corrosion, and weight penalties. Composite materials offered the potential for lighter structures, longer service life, and reduced maintenance, making them attractive for next-generation aircraft. The Boeing 787 extensively uses carbon fiber reinforced polymer, CFRP, for major structural components, including the fuselage, wings, empennage, and floor beams. CFRP consists of high-strength carbon fibers embedded in a polymer matrix, providing excellent stiffness, fatigue resistance, and corrosion immunity. Limited use of glass fiber composites and titanium alloys complements the composite structure where required. Unlike traditional aluminum fuselages, assembled from multiple skin panels, the 787 employs large composite barrel sections. These barrels form a semi-monocoque, stressed skin structure, with composites carrying both primary and secondary loads. The wings are also primarily composite, allowing high aspect ratio, flexible wings that improve aerodynamic efficiency and reduce fuel burn. The introduction of composite structures required advanced manufacturing techniques such as automated fiber placement, AFP, resin curing in autoclaves, and precision layup processes. Large integrated structures reduce the number of fasteners and joints, improving structural efficiency and lowering maintenance demands. Quality control relied heavily on non-destructive inspection, NDI methods, such as ultrasonic testing. The use of composite structures in aircraft offers several significant advantages over traditional aluminum structures. One of the most important benefits is the substantial reduction in structural weight, which directly contributes to improved fuel efficiency and performance. Composites also exhibit excellent fatigue and crack resistance, as they do not suffer from the same crack propagation mechanisms as metals. Additionally, composite materials are inherently resistant to corrosion, eliminating a major maintenance issue associated with aluminum airframes. Their superior structural behavior allows higher cabin pressurization levels, enabling increased humidity and lower effective cabin altitude for improved passenger comfort. As a result of these characteristics, composite aircraft structures generally require reduced maintenance over their service life. Despite their advantages, composite structures present several challenges that must be addressed in aircraft design and operation. The initial manufacturing and certification costs are high due to advanced materials, specialized equipment, and stringent quality control requirements. Repair procedures for composite structures are more complex than for metallic structures and often require controlled environments and skilled technicians. Composites are also sensitive to impact damage, which may not be visible on the surface, but can significantly reduce structural strength. Furthermore, advanced non-destructive inspection techniques are required to detect internal damage, and the introduction of composites has necessitated the development of new design standards and certification approaches to ensure long-term structural safety. The extensive use of composite structures allowed the Boeing 787 to achieve improved fuel efficiency, longer range, and lower operating costs compared to conventional aluminum aircraft. The aircraft supports higher cabin pressure differentials and humidity levels, improving passenger comfort while maintaining structural integrity. The Boeing 787 fundamentally changed aircraft structural design by proving that composites could be used reliably in primary load-bearing structures of large commercial aircraft. Its success influenced subsequent designs, including the Airbus A350, and marked the beginning of a new era in aircraft structures dominated by composite materials.